Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. I have Dr. Takuya Segawa. He's over in Zurich, Switzerland, at ETH Zurich, and we're going to talk about his work in solid-state physics. He's working on a sensor that can go inside, looks like individual cells, to monitor their conditions. So, Takuya, thanks for coming.
Thank you very much for the invitation.
Yeah, if you would, tell me about your research. What are you working on?
So maybe first my background. My background is magnetic resonance, and this is best to know to the like everyday life. These are these machines in the hospital, these MRI machines, magnetic resonance imaging, where you can put your head in or your knee or your whole body, and you see actually the water inside. And what you really see are so the water is a chemical molecule, H2O, and what you see are the spins, nuclear spin. So these spins are quantum physical property of nuclei or electrons. And you're looking at these nuclei, and these are very, very small things. They are magnetic and they are precessing. So you have to put them in a very strong magnetic field, put in some radio frequency to disturb them, and then you get a signal you can record inside these coils. And that's a revolutionary thing, revolutionized medicine, also analytical chemistry. But basically, the weak part of this technique is it's very, very insensitive. You need millions and millions and millions of spins that you just get one pixel or one voxel in this MRI image. And a few years ago, maybe about 25 years ago, a scientist in Germany, Stuttgart, Professor Rachtrup, discovered that with a technique, it's an optical technique, it looks like a microscope. You can look at an individual spin. And this is now a totally different system than water. It's diamond, and inside this diamond crystal is a defect, but a very special defect. Okay. It's a nitrogen atom replacing a carbon atom, and next to it, the vacancy, so a missing carbon atom. And this has an electron spin, and this is also fluorescent. So if you shine on green light, it emits red light. And the special property is this fluorescence is connected to these spins. So if you manipulate the spins with radio frequency, you can see a change in the fluorescence. Actually, the fluorescence gets darker. And this experiment is so sensitive that you can detect a single spin. So that's kind of the beginning of the story.
So it's literally millions of times more sensitive than how you'd use an MRI?
It's it's probably like 17 orders of magnitude or something like that more sensitive. So that's a number which is, you don't usually hear this in physics because it's so large. And it's just you profit actually you profit from the photons of this visible light. So there are two transitions. So in quantum mechanics, we're looking at, as the name say, quantized energy levels. So you have energy levels which are quantized for these spins. This is a very small gap, and then you have this huge gap which is visible light, which is connected, and with that you can profit from a huge gain in sensitivity. And the next step is you can put this defect into nanodiamonds. So it's also a diamond, but only of a size of a few to maybe 100 nanometers. And with that, you have something, you have basically a nanoparticle. You can do MRI on it. So these are the two, let's say, basic ingredients of this story.
Did you discover this, or how did you first encounter this, nanodiamonds and being able to do this?
I was in contact with a group in Japan, Kyoto University, and I think this was one of the first group which moved from this classic magnetic resonance, NMR, to this direction of nanodiamonds. So this was a Professor Shirakawa at Kyoto University. And so what these spins, they do, the nice thing is, you can use them as a sensors, coming to the topic of the discussion today. So this magnetic resonance signal changes. For example, if you apply a magnetic field, you have two signals which split, and if you look at the distance of this signal, you can read out the magnetic field. Or you can look at other things like temperature. This line also shifts with temperature. And you can look at the position, the orientation of this nanodiamond with respect to the magnetic field.
So if this was inside of a cell, a living cell, like a bacteria or a human cell, could you tell temperature? Yeah. Could you tell position? Like, what could you tell?
Yeah, so the nice thing of these nanoparticles is that they are not toxic for these cells, because there are also other nanoparticles like quantum dots. Often some cells die if you put them into it. But these nanodiamonds, they are not toxic. And so let's say this field, I would say it's really at the edge of becoming a real application, hopefully, for biologists. So at the moment, we're still at the stage that we're improving the sensitivity to really bring it to daily tool, like for example, the green fluorescent protein biology. So every cell biologist is using this GFP. There was a Nobel Prize for this, and there are so many variants. Yeah, you can use measure. Yeah, also like pH or other things with some mutation.
Yeah, it's like green fluorescent protein.
The nanodiamond. So one hope is, of course, that's better than it. And one thing of all these, let's say, fluorescent molecules is after sometimes they bleach. So if you shine on some laser light, after some time they just go out, because there is the energy of this light basically changes the structure of the molecule, and this turns the fluorescent molecule in a dark molecule.
How big is the nanodiamond versus GFP? How much smaller is it?
Yeah, that's where we're currently totally losing, because the GFP, this is really, let's say, a larger molecule. So it looks a bit like, it's a bit longer, like the length is maybe about 5 nanometers and like a diameter of about 3 nanometers. And so currently the most people doing these in-cell experiments probably use something like 100 nanometers in size. And of course, there are many of these NV centers, because a single NV center is also darker than GFP. So you need many of those that you have a decent fluorescent signal. So one research direction I'm trying is to bring these nanodiamonds to a smaller size. And there are actually nanodiamonds which have a size of 5 nanometers and are quite spherical. And their origin is a quite funny story, because they're called detonation nanodiamonds, because their synthesis is detonation. And it's really like, munition from the military, from the army. It's TNT and some other chemical. You explode this, you have an explosion inside the container. There is no additional source of carbon. And then there's, of course, a lot of ash and many things. But if you purify this, you find these very small nanodiamonds. And there is this shockwave of this detonation. And during the shockwave, there is a temperature and a pressure which is enough to make these small nanodiamonds.
So that's how they're made, is with controlled mini detonations. Nanodiamonds are made by doing these mini detonations in the absence of extra carbon, I guess in the absence of oxygen, in these vessels. And you can control the size of the nanodiamonds.
So it's interesting. I think very often what really comes out is the size of these 5 nanometers. This seems to be some chemical stable region. The problem is that you first have to get them down to these 5 nanometers, because they aggregate very, very strongly. So a long time ago, like not so long time ago, people didn't know that the core size is 5 nanometers. So there was a discovery from also a Japanese professor who put a lot of high power sonication and some beads, some zirconia beads, to really disperse those particles. And then he found that kind of this stable small size is 5 nanometers.
Even visualizing 100 nanometer objects is difficult. How do you manipulate and visualize a 5 nanometer object? I mean,
we visualize. You can look at the electron microscope image. If you want to check that it's really 5 nanometers, you can measure for a bulk sample in solution. You can measure dynamic light scattering, and so these particles are swimming in water, and depending on how small these particles are, so you have a different type of scattering, and with that you can calculate the size. And So we have taken those very small nanodiamonds, and interestingly, without doing anything, there are already these defects we want, these nitrogen vacancy centers or NV centers inside. So somehow during this detonation reaction, they must be created. And actually, we can also put more of these defects inside by doing some electron irradiation. So we go to some source which can bombard some electrons. These electrons, they create some vacancies, so they have a high kinetic energy. They kick out some carbons, and with that we see some formation of these NV centers.
Yeah, how do you make sure that you have the right defect that you want?
Of course, there is always probably also produce other defects like only vacancy or vacancy pairs. But this NV center has this magnetic resonance signal appears at the very characteristic frequency. So it appears at about 2.87 gigahertz. So that's something which is, let's say, quite close where your wireless internet or so is emitting your data. And if you see this peak in this special microscope where you detect the light and at the same time you emit some radio frequency of this frequency, then you really know you have this NV centers inside.
I was going to joke with you and say, if you ever want to get married, don't give your fiance a nanodiamond.
Yeah. I agree. That also came to my mind. Yeah. So often people, I also when I started in the field, I ask like, these nanodiamonds, are they maybe expensive? But they're really cheap. Any like drug or so is much more expensive per gram. So the synthesis is really cheap, this detonation. But then like if you have to deaggregate them, I think they're still cheap. But if you have to do the electron irradiation and maybe then still as a next step, you want to functionalize the surface to stabilize them from aggregation. That's either a lot of or some work in the lab, or if you then want to buy it from a company, then it's getting a bit more expensive. But the diamonds themselves, they are really cheap. Yeah.
So what's the end goal? You would put the diamonds in a vesicle and have them enter the cell, or? Yeah,
so it really depends on the type of the cell. Usually the easiest thing we're working with are, let's say, human or mammal cancer cells. So I'm not the cell specialist here. I'm collaborating with some people who really know what they're doing. And these cancer cells, they basically eat everything. So it's easy to let them eat the nanodiamonds. And then as you say, then there are in these vesicles. And the other option is you can apply a technique called electroporation. So that's really an electroshock. You have your cells in your buffer solution, and you switch on a high voltage for a very short time. And in that time, the cell membrane, speaking of mammal cells, will open probably like 100 nanometers or a few hundred nanometers through this shock. And in that time, let's say your nanodiamonds, if they're in the solution outside, they can stream into the cells. And that's another options to bring in the cells. And if you do that in a very controlled and optimized way, the cells will close again their membranes and happily continue to live, and they will not die. And you can do some measurements.
So how many nanodiamonds would you want inside a cell? And then would they disperse evenly? And what would you measure?
As long as you just want to have a nanodiamond inside and like proof of principle want to measure something, you're happy with one nanodiamond. It's better than having too many, especially when they are aggregated. If you are good in chemistry, or if you have some collaborators who are good in chemistry, you can try to do some targeting, which is also know from other experiments, like if you tag some antibody or some peptides which like to go, for example, to some dock on some membrane or so, you can also guide them inside the cell and have them at a special point. And then, let's say you want to measure the temperature inside the mitochondria, you can do this in this way.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
Well, how close are you to measuring anything inside cells? Are you at that point yet, or is it still going to be a while until this is figured out?
We're able to bring the nanodiamonds inside the cells. Let's say for temperature, I think for a long time the problem was to get the sensitivity, let's say, smaller than one degree or one Kelvin. Yeah, then you can measure temperature, but if you only see a shift of let's say 10 degree or 10 Kelvin, I mean, that's not some natural behavior of the cells. So you would have to do something to heat them up. But recently there are really some advancements in the field, just optimizing these experiments where you can really get down to, let's say, 0.2 degrees, recent paper. So there is a lot of hope that soon there can be some really biologically relevant experiment. But I really have to say at the moment there is no killer application yet that really the biologic community would have realized, I think, about our experiments. I think they don't know about these nanodiamond experiments yet.
Well, what do you call it if you're going to put these inside of a cell? I mean, what do you call them? Just now, I mean, if I look up papers on it, will I just look for nanodiamond biology applications, or how would you search?
So nanodiamonds, certainly the defect is the nitrogen vacancy, or NV center. So if you say NV center, probably everyone in physics today will recognize this term, because in physics it's quite the hot field, and also there are a lot of research groups working on it. And the other thing is word is quantum. Some people call this quantum sensing. Yeah, I think everything is quantum at the moment in physics. So quantum computing and quantum Internet of Things, quantum cryptography. And what people don't really speak so much about is this quantum sensing, where you use, like a spin, a quantum system, and you see the change of this transition. So if you do spectroscopy, you see some lines, these transitions. There are some lines at these given energies, and these lines shift when, for example, the temperature shifts, and this is called quantum sensing. And I think these nitrogen vacancy centers and nanodiamonds are really good examples where one could do, or one is already there to do some nice quantum sensing. So maybe these three terms.
So you can see temperature changes, and they're getting it down to a small range. What other changes? What else could we see inside of a cell?
The other thing would be that, for example, you could look at radicals or pH. So, for example, with my colleagues in Japan, published a paper about pH. So depending on the chemistry, there are different chemical groups, functional groups outside the nanodiamond. And so, for example, there are this COOH or carboxylic acid groups, and the relaxation, so the decay time of your magnetic resonance is different if this H atom is on these acid groups, or due to pH change, it goes into the solution. So you can basically measure two pH ranges, so above a certain pH and below a certain pH. However, this was not yet in cells. This was an experiment or a proof of principle outside cells. And the other thing I think also for biology would be relevant would be radicals, because even we hear daily about radicals, what are radical quenchers, or what's good food to kill your radicals. So radicals are also basically there is an electron spin on these radicals, because there are unpaired electrons. Usually electrons are paired in chemical bonds, in covalent bonds, and that's what they want to do. But if they are alone, they are unpaired, and that means they are very reactive, because they don't like the situation. They look for other molecules to get an electron, and then this molecule becomes the radical. And if this molecule is a DNA or so, then maybe this is a mutation of your genes. So it can be something risky, maybe leading to cancer. So if you could use these nanodiamonds to check if the number of radicals is constant or increasing or not. And this is something you could do because your NV centers has electron spins. These radicals are electron spins, so they should kind of feel each other through their magnetic fields. And if you could use that as a sensor, and there are, I think, maybe not yet something published, but a colleague of mine, Romano Schierhagel in the Netherlands, presented some results. I think this could be something very interesting for also the biology or the medical community.
How many would you want in each cell? I mean, you wouldn't just want one. I would think, if I want to know the temperature inside of a cell, it'd be more interesting to have an array of, let's say a dozen of them at different points of the cell, or 100 of them. Same with the radicals.
Yeah, yeah.
Like to see the
So
profile.
yeah, I agree. One that would be one approach, and the other approach would be you have one, and this one is traveling through the cell, and then like time resolved, you can see some changes. You look at some changes of the cell, like cell aging, and then you see how these properties are changing.
Or if a whole bunch of cells have one each, then you could look at the variations amongst the population of cells.
Yeah, yeah.
When they enter a cell, does anyone know where they go? Do they migrate out of the cell, or do they go to a certain place?
Yeah, yeah. So with the again, I think it depends on the way how they are incorporated into the cell. So if they go into these vesicles, I think there is some mechanisms where they are again kicked out of the cell with these vesicles. I think is about an order of, I think, on a day or so.
So they only last like a day in the cell, and then they come out in the vesicle.
Yes, if it's this way that they are entering the cell with the vesicle. If it's with the electroporation, sometimes they really stick to some membrane of an organelle or some. Basically, they stay there.
What about if they're eaten? You gave an example of like a cancer cell eating.
Yeah.
A nanodiamond. What happens then?
I'm not sure. Maybe they keep them. Maybe they. I don't know if they accumulate though.
There's different methods, and if your goal is to keep it inside a certain spot in the cell.
Yeah, I think for that the electroporation, the electroshock method is the best. Yeah.
Oh, okay. So is this going to be tested first in bacteria, or what kind of cells?
Yeah, I think this human cancer cells is what we're working with. But you can also take bacteria. Or so what is more difficult is if there are some kind of plant cells, because then you have additionally a cell wall. So that's a bit more difficult to overcome. Yeah, in principle, there are also is the possibility to take a micropipette if you have really a large cell, and put them into the cell with a pipette. So that's like artificial fertilization. So you could take the same tools.
I could see in a dish you could do this, but in a person, how would you do this? You'd have to, I guess, put the nanodiamonds inside of a population of cells and then inject them into the person.
Yeah, the problem is, I think putting in nanodiamonds, maybe you would still find a way. But our detection method is really, we kind of have a microscope, a fluorescence microscope, which collects the light, the red light these defects are emitting. And if you're really inside the body, this light will not go through your. Yeah, you cannot look inside a body like you can do it for MRI. So this is really limited for single cells, transparent small animals like these worms, C. elegans, or maybe fish. But we cannot replace MRI in that sense, because our skin will block this light. So first the laser doesn't go in, and then the fluorescent doesn't come out.
Oh, very tricky. But it would still be very useful for lab work, though. Yeah.
So the thing would be like for this temperature. When I speak to some biologists, so it seems like temperature is a hot topic for biologists at the moment. Like, well, what's the temperature inside the cell? And there are different methods, and the results are sometimes really totally inconsistent. So no one knows what is correct. And what they really don't know is like what is really the nanoscale or maybe sub-microscale temperature resolution. What's the difference like inside mitochondria or outside mitochondria? So this is something really they don't know, because there is no nanoscale temperature sensor, which is good enough.
Gotcha.
So that could show. I mean, if you measure temperature as a physicist or chemical physicist, you can go towards thermodynamics. So you can go really to another level of understanding of a cell. This would be, if we could reach such a level, this would be certainly lead to a lot of new understanding. Yeah.
Well, very good. Takuya, how long do you think this will be commercialized and available for use?
So commercialized, there are two companies which are producing such nanodiamonds. There is one in the US, there's one in Taiwan. So there is already some market. However, if you only have the nanodiamond, that doesn't help you, because you still need a setup. And so this is a microscope. Basically, the microscope part you can buy. You can buy like a Nikon microscope or so. But the other part, the microwave part, that at the same time you have to do a magnetic resonance experiment, this really, I think, is not yet commercialized. And I think if once there would be a killer application, or this would be so successful that the biology community would acknowledge this and start using it, I think there would be really a need for also production of these setups, because at the moment people doing these experiments, they build their setups by their own. So you have to be an engineer or some physicist, and people doing biology, really the experts on these cells, they will usually not do this. So I think if some success will come, there will be some market. But yeah, we'll see what the future brings.
Well, very cool. Well, Takuya, thank you for coming on the podcast. I appreciate it.
Yeah, thank you very much for the nice talk.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.